We'll be learning two theorems today. So one is called the mean value theorem, and then one is called the Rolle's theorem. So Rolle's theorem is actually a corollary of the mean value theorem. It's actually a special case of the mean value theorem. So let's start out with Rolle's theorem. So the way I memorize this is I always remember that it's rolling hills. So rolling hills always have maximums and minimums, right? What is the slope at the top of a rolling hill? 0. Okay, that's the way you're going to remember Rolle's theorem. Okay, so Rolle's theorem has three conditions. Now, every time you use these theorems, you have to list the conditions in order to use them. So if you said, oh, this is true by the mean value theorem on the AP test, but you didn't say f is continuous, f is differentiable, and so on, you wouldn't get any points. Okay, so you have to say the conditions. So Rolle's theorem, it says, let f be a function that satisfies the following three hypotheses. So number one, f is continuous on the closed interval a to b, and f is differentiable on the open interval a to b. Okay, the reason we say an open interval, and we'll talk about this in a little bit, but an open interval, on these endpoints, there's actually not a derivative. So you can never take the derivative of an endpoint. Do you guys remember our definition of derivative? It involved limit as you go from the left and the right. There's nothing coming from the right on this one, and there's nothing coming from the left on this one. Okay, so it's not differentiable on the endpoints. So that's why we say on the open interval. And then the other condition is that f of a has to equal f of b. So if this is true, then there has to be a number c in the interval a to b such that f prime of c is equal to 0. Okay, so you guys have a sketch of this. So basically, we have a continuous function, so I don't have any holes, I don't have any asymptotes. I'm connecting 2 points that are at the same height. So f of a is equal to f of b. So when I connect those 2 points, there has to be a place somewhere between them where my slope is equal to 0. Okay. Where the slope is equal to 0. So f prime of c is equal to 0 there. So, I mean, you can have more complicated drawings. So maybe I have something like this, right? But these are at the same height, right? Then there's multiple places where my slope was equal to 0 between a and b. Do you guys see all those? So if you're at the same height, so if the endpoints end at the same height, then there has to be a place where you had to, what goes up must come down, right? If you go up, you have to come back down, so there has to be a place where you level off. Why could it not be like this? What was the condition? Not the continuous one. It's not differentiable. That would not be differentiable, right? So as long as we have a nice, smooth, rolling hills, we will have a place where our slope is equal to 0. All right, so number 1 says, find all numbers c that satisfy the conclusion of Rolle's theorem for f of x equals x cubed minus x squared plus, or minus 6x plus 2 on 0 to 3. Okay, so we're going to practice writing out these conditions. So the first thing, f is continuous. Why do I know that that's a continuous function? Like it's a polynomial, is that what you're saying?
Yeah.
Yeah, it's a polynomial. I never have a place where I have like undefined, right? No square roots, no denominators, so it's continuous. F is differentiable on 0 to 3 as well, but we don't include the endpoints this time because, like I said, you can't take the derivative of an endpoint. There's no slope there. Okay, and the last condition says that f of a equals f of b. So let's try. So let's find f of 0 and let's find f of 3 and see if they're equal to each other. So f of 0 is going to be 0 cubed minus 0 squared minus 6 times 0 plus 2. It's all equal to 2. And then f of 3 is going to be 3 cubed minus 3 squared minus 6 times 3 plus 2. So we get 27 minus 9 plus 18 plus 2. Ah, dang it, I did that in the other class too. Minus 18. And that equals 2 as well. All right, so we get that f of 0 is equal to f of 3. So we have satisfied all three conditions. F is continuous on the closed interval, differentiable on the open interval, f of 0 equals f of 3. All right, so now we can use Rolle's theorem. So we can say, well, there has to be a number c on that interval, so some number between 0 and 3 where my slope equals 0 at that point, okay? So I'm going to find my derivative. F prime of x is equal to 3x squared minus 2x minus 6, and I set it equal to 0. So you can try to factor. It doesn't factor. You can try to. It doesn't work. So I tried to in the last class, but I won't in this one. So if we want all of this equal to 0, then we're going to have to use our favorite quadratic formula. So I'm going to do x equals negative b, so 2, plus or minus the square root of b squared is 4, minus 4 times 3 times negative 6, all over 2 times 3. So I get 2 plus or minus 4 plus 72, so 76. So 2 plus or minus the square root of 76, all over 6. And you can find the decimal version of those if you want. So the first one, when I plug in positive root 76, I get x equals 1.786. And when I plug in the negative root 76, I get negative 1.120.
But that's not there, it's on an interval.
Exactly. It's not on our interval, so we cross it out. So our solution, our value c that satisfies, would be c equals 1.786. That's our answer. All right, do you have to write c equals? I don't care. You can write x equals. It's fine. Okay, does that all make sense? So we're going to go through the same process for this one. So it says determine if Rolle's theorem can be applied. So we want to show that it satisfies the 3 conditions. And then we want to find f of negative 2 and f of 2. Okay, see if they're equal. And then find the value c by doing f prime is equal to 0. All right, so is it continuous? Yeah, because it's a polynomial, right? We just said polynomials are continuous. So continuous. It's continuous everywhere, but definitely continuous on negative 2 to 2. It's also differentiable on the interval negative 2 to 2, open interval. All right, so we find f of negative 2 and we find f of 2. F of negative 2 is going to be positive 16 minus 2 times 4, so it's going to be 8. Do you guys see that 2 would be the same thing? It's also equal to 8. So f of negative 2 is equal to f of 2. So we have our 3 conditions. We're continuous on the closed interval, differentiable on the open. We have f of 2 equals f of negative 2. Okay, so that's all like before we've even really started the problem, right? We've never even like set f prime equal to 0 or anything. So now we do the second part. So we say, okay, well, what is f prime? F prime of x is 4x cubed minus 4x. So when I set it equal to 0, I can pull out the 4x and I have x squared minus 1. So continue to factor, we have x plus 1 times x minus 1. So we get 0, negative 1, and 1. Are any of those on the interval? All 3 of them are on the interval. So this is one that has more than one answer. So the theorem just says at least one place. There has to be at least one place. This one has 3 places. So you can write c equals or you can leave it as x equals. It's fine. All right, making sense? All right, so if you guys had something, I didn't write this, but what if I had like f of x equals x over x minus 3, and I said we were on the interval negative 1 to 5?
No, because f3 is not 3,
It's not continuous at 3, so you wouldn't be able to use Rolle's theorem. So even if you found 2 values where you had f of a equals f of b, you wouldn't be able to do anything because it's not a continuous function. Okay. So if that happens, those are kind of nice because then you're just done. You don't have to do anything else. All right, so the mean value theorem. So this is the more general form. So the Rolle's theorem is a very specific case of the mean value theorem. So it says let f be a function that satisfies the following hypotheses. So the first 2 are the same. F is continuous on the closed interval, f is differentiable on the open interval. It says then there is a number c in a to b such that f prime of c is equal to, mean. Mean in math means what? Average. What average equation do we know? Average rate of change. What is the average rate of change? It's the f of b minus f of a all over b minus a.
And so that is, there's a number. Can there be more than one?
There can be more than one, just like with Rolle's theorem. There is at least one number c, such that that is true. All right, so here's the sketch of the mean value theorem. So it's similar, but now f of a and f of b are not at the same heights. Okay, so if they're not at the same height, all we do is we connect them, and we're like, okay, if I connect these 2 points, then I have a certain slope. My slope would be the y2 minus y1 all over x2 minus x1, right? F of b minus f of a all over b minus a. And there has to be at least one location where my slope of my tangent line is the same as the slope of that line, okay? Of a tangent line just barely touches. So this is the same slope. So there has to be at least one place where that's true. Now, does it have to be one place? No. So if I had some kind of curve like this, and I connected my two endpoints, I'm like, okay, there has to be a tangent line that has that same slope. You can kind of estimate tangents. This one definitely doesn't have that same slope. This one doesn't have the same slope, right? But there are places where they are the same. So like right there, right there, right there, right there. Those all have the same slope. So there can be more than one. Does it make sense? So there is a real-life application of the mean value theorem. So let's talk about that real-life application. So let's say I'm driving my car, and I go a total of 120 miles. And it takes me 2 hours to drive that 120 miles. What was my average speed? 60 miles per hour, right? So on average, my velocity was like 60 miles per hour. Now, did I launch myself out of my garage going 60 miles per hour and maintain that speed until I got to my final destination?
Probably not.
No.
That's what I do.
Did I go over 60 miles per hour? Probably, because I couldn't launch myself out of the garage at 60 miles per hour. So at some point, I probably went over 60 miles per hour, right? But at some point during the trip, did I go at exactly 60 miles per hour? Yes, I had to. Does that make sense? Because I can't go from 50 miles per hour and magically leap to 80 miles per hour without going through 60 miles per hour. Does that make sense? That's the mean value theorem. So the mean value theorem says that you have every single rate of change. So every rate of change occurs at least once in between two values, okay? So you have to have that velocity somewhere, at least once. Okay, so that's what I was saying here. So for instance, if a car traveled 120 miles, the speedometer must have read at exactly 60 miles per hour at least once. So how are Rolle's theorem and mean value theorem related? So I told you that mean value theorem was the more general one, and the Rolle's theorem was a very specific example of mean value theorem. So tell me why. So what was special about Rolle's theorem that we didn't have for mean value theorem? F of A is equal to F of B. So the mean value theorem says that f prime of C is equal to f of B minus f of A all over B minus A. And what if f of A is equal to f of B? What does all of that become? 0. It becomes Rolle's theorem, right? It becomes f prime of C is equal to 0. That was the Rolle's theorem. Do you guys understand what I'm saying? So since f of A and f of B were equal to each other for the Rolle's theorem, then really the f prime of C is just equal to 0 anyway. Okay, so that's why it was a very specific case of the mean value theorem. So really, if you just know mean value theorem, you're fine. You would be able to, you'd do well on the test. You could always just say using mean value theorem, but I think you'd really impress the graders if you instead used the correct term and we're like, oh, this is the more specific case. This is Rolle's theorem. Right, so kind of know the difference.
Does impressing them potentially get you extra points?
Of course. No, not really. They are very specific in their grading. Brownie points for me, for sure. All right, so find a value of C satisfying the conclusion of the mean value theorem for f of x equals x cubed minus x on the interval 0 to 2. So we started out the same way. So we say f is continuous on the closed interval.
Are you going to make us write this on everyone? Or
Yes, I am. I count you off on your test.
Can we abbreviate?
How am I abbreviating it? Continuous differentiable. So cont diff. All right, so on your test, basically you get a point for having this, you get a point for having this, right? If you don't have those, do you get those points? No, you don't get those points. Right, and so now the next part says f prime, so f prime equals the average rate of change. So we're going to do f prime of x, and that's 3x squared minus 1. And we want to find the average rate of change, ARC, average rate of change. So we're going to need to find what f of 2 is and what f of 0 is. F of 2 is 2 cubed minus 2, so 6. F of 0 is 0 cubed minus 0. which is 0. So my average rate of change, that f of b minus f of a all over b minus a, is f of 2 minus f of 0 all over b minus, or 2 minus 0. So it's 6 minus 0 over 2 minus 0, which is 3. So the thing that people will mess up on their homework and on the test is they always set the derivative equal to 0. We're not setting the derivative equal to 0 in this case. We're setting it equal to the average rate of change. We're saying 3x squared minus 1 is equal to 3. So we took that value that was right there and we plugged it in for f prime. So we get 3x squared equals 4. X squared equals 4 over 3. We take the square root of both sides. We do a plus or minus. So we get x equals plus or minus the square root of 4 over 3, or you could have 2 over root 3, or you could have 2 root 3 over 3. It doesn't matter. Yeah, or you could have the decimal approximation, 3 decimals, rounded or truncated. So, what is our value of c then? Just the positive one. That is the only one that's on the interval. That's the only one that we're worried about. We don't worry about any other interval. Okay? So that's it.
I like
Hmm?
with the Rolle's theorem, the f of something is equal to f of something. Do we have to write a better thing?
We don't. So we don't need f of a is equal to f of b because they aren't equal to each other, right?
So we just don't have to write.
We don't, but we do have to find what the average rate of change is. So that's what we did right over here. We found the average rate of change. So show that somewhere. All right, so number 2. So determine if the mean value theorem applies to f of x equals 2 minus 3 over x on the interval 1 to 5. So 2 minus 3 over x is not always continuous. So what do you think, Julia?
So I was just
Yeah, question?
So if we find that the mean value theorem applies to, or that the Rolle's theorem applies to the equation, does that automatically mean that the mean value?
Yes. So if the Rolle's theorem applies, then that means that the mean value theorem applies. Okay. So Rolle's theorem is a specific case of the mean value theorem. All right. So we have 2 minus 3 over x. Where is this not continuous? It's not continuous at 0. So f of x is not continuous at x equals 0, but
It doesn't matter.
f of x is continuous on 1 to 5. So really, you would not need to write f of x is not continuous on 0. I mean, as long as you recognize, okay, that one's not a concern anyway. Okay, so f is continuous on 1 to 5, so we're good there. F is differentiable. Oh, I don't know. Let's take the derivative. So if I have f of x equals 2 minus 3 over x, it's 2 minus 3x to the negative 1. So its derivative is 2 plus, not 2, sorry, it's plus 3 x to the negative 2, or 3 over x squared. That is also not differentiable somewhere. Where is it not differentiable?
Yeah.
Nope, it's positive. Negative 1 goes to the front, it's positive. All right, so it's also not differentiable at 0. But is 0 a concern to us? No, so we're good. So f of x is continuous. Or not continuous, sorry, differentiable. I already said continuous, didn't I? Differentiable on parentheses 1 to 5, parentheses. So that's our second one. So that's all I need for mean value theorem, those two things. Okay, I'm going to find the average rate of change. I'm going to set it equal to the derivative. So I want to find where f prime of x is equal to f of b minus f of a all over b minus a. So in order to find that, sometimes it's nice to kind of do some things off to the side. We want to find f of 1 and f of 5. They're not pretty. F of 5 is 2 minus 3 fifths. So we have 10 fifths minus 3 fifths. So we get 7 fifths. And then f of 1 is going to be 2 minus 3 over 1. So 2 minus 3, that one is pretty. Negative 1, right? So we have 7 fifths minus a negative 1 divided by 5 minus 1. And that's all equal to our derivative, which was 3 over x squared. So what do we get on the top? We have 7 fifths plus 1 12/5, yeah. So 12/5 divided by 4. So what is 12/5 divided by 4? 12/20ths. Or you could flip it and then reduce, so 3/5. Yeah, or you could just take the 12 and say, oh, I have 12 out of 5, so if I divide that 12 into 4 pieces, I'm going to only have 3 out of 5. So I have 3/5. So this is all 3/5. So I get 3 over x squared equals 3/5. You could do all that cross multiplication stuff, but you could also just realize that 3 over something equals 3 over something. So what is x squared? X squared is 5, so x equals plus or minus the square root of 5. So when it says find the value of c guaranteed by the theorem, it's just the root 5. So it says, if the theorem does apply, find the value of c guaranteed by the theorem. Visually, what is the mean value theorem trying to find? Draw it in. So here's where our 1 value is. 1 comma, what was it, -1? These are going by, I hate when I do that, -1s. All right, and then the other one, 5 is going to be at, what was it, 7/5? And that was the point 1 comma -1. So visually what we're doing is we're connecting those 2 points and we're finding a location where we have exactly that same slope. It looks like it's right around there, right? That x value, if I drop it down, is a little bit more than 2.2. That's what root 5 is. So root 5 is not exactly 2.2, but it's right around, yeah, 2.236. Somewhere around there. Okay? Does that make sense? All right. So explain precisely why we cannot apply the mean value theorem for the functions below on the provided intervals. Yeah, so what do you think, Ian?
For number 1, it's because it's not differentiable at x equals 3.
Yep, exactly. Not differentiable at x equals 3. I don't know exactly what that graph looks like. It might be interesting to see what it looks like. Since it has an absolute value, it's probably going to involve some kind of like corner, right? So let's see what it looks like. Let's graph it.
How do you do absolute value on these again?
Yeah, I'll just put it on grapher instead of my normal. What is the what? Oh, you can use the app, yeah. 3x minus abs x minus 3. Oh man, maybe I should do it on my regular calculator. Wabbit. All right, so go ahead and graph this, guys. Get your calculators out. Try it with me. I'm just curious as to what it looks like. I didn't know what this graph looked like, but
It seems to be a line that starts to curve at some point. It seems to be a line that becomes a curve. Oh no, that's a corner. That's just a corner. It's a very, very broad corner. It's like 150 degrees or something, a really broad corner.
all right, so I got to go up, huh? So let's go up to like, let's do 50. Is that too tall? Yeah, it does kind of turn. But yeah, it's not actually differentiable there. So it doesn't really look like a corner very, very much, but it is actually a corner. It's like a weird like corner cusp thing. But that occurs because of the absolute value. Okay. Yeah, it's because inside that, like if I didn't have that 3x, so if I ignored the 3x and I just cover it up, then we know that this graph would look like the absolute value function. It would just be shifted to the right 3. So it would start out at 3. Does that make sense? Yeah, so when you have that 3x minus all of that, the minus flips it over, and then the 3x is adding like a line to it. So you're still going to end up having a little bit of a flip to it. It's like doing the line and then adding on that new function. It's kind of weird. All right, so it's not differentiable at x equals 3 because there's a corner. I was just curious what it looked like. All right, and then g of x equals 2 over x plus 2. So if I have the interval -3 to 1, what do we see about that?
-2.
What about -2?
Not
-2 is an asymptote. A vertical asymptote. Do you guys see that? So it's x equals, it's not continuous or differentiable at x equals -2. and that's on that interval, so we can't use mean value theorem for that. And then this last one, x to the 2/3. Do you guys remember what that looks like now? It's a good one to put on a flashcard. It's right there on the board, yeah. So I did it at the beginning of class. It looks like this. Now, if you did not know that one, then it's like, oh, wait, it could. It looks like it's continuous. There's not a place where we have a denominator or square root, right? So it looks like it's continuous. But if you actually try to find the derivative, you get 2/3 x to the negative 1/3, which makes it 2 over 3x to the 1/3, like that. Okay. Which you can't have 0, right? So 0, well, let's say h prime of 0 is undefined.
So it's not differentiable at 0?
Yeah, exactly. So it's not differentiable at x equals 0. Mathematical spelling bee, differentiable. Can you guys do it? All right, so let's do the last little bit. So the last little bit involves something called antiderivatives. Antiderivatives, yes.
These are anything as complex as antiprotons were in trouble.
Everybody signed the petition.
You're against derivatives? Oh, you're
Yeah,
so cheeky,
and now you have
Alex.
to do something that's probably harder. So.
All right, so important corollaries from the mean value theorem. So it says if f prime is equal to 0, so if I take the derivative of a function and I get 0 out, what do I take the derivative of to get 0? Like 1, 7, any constant, right? So then f of x equals c for some constant, c in the interval, or for all x in the interval. All right, what if f prime is equal to g prime? Can you think of two functions that when you take the derivative of them, you get exactly the same thing? X and what's another one that you take the derivative of and get 1 out? So how about x and x plus 7? Do I take the derivative of both of those and get 1? Yeah, so it says then there's some constant c such that f of x equals g of x plus c. So as long as they're differing by just a constant, when we take the derivatives of both of them, we get f prime equals g prime. So number 1 says find the function f of x whose derivative is cosine of x. So what function do I take the derivative of and get cosine of x?
Negative sign.
Right, so if I have f prime of x is equal to cosine, then if I go backwards and I say, well, what's f of x? Then it would be, is it negative sign? You guys were saying negative sign. It's sine. I take the derivative of sine to go back to take the derivative and get cosine, right? But is that the only thing that has that derivative? No, I could have sine plus 2, sine plus 8, sine plus 2 pi, right? I could have lots of things. So we put a c. Now the second part of the problem says whose graph passes through the point pi comma 5. Shh, Jordan. So if you have pi comma 5, we want to plug in pi for x and get 5 for y. So 5 equals sine of pi plus c. What's sine of pi? 0. So what's c? 5. So our function, our final function, is not f of x equals sine of x plus c, but sine of x plus 5. We just found c. Okay, so what do? We involved the opposite of derivatives, right? We went backwards. That is what the entire second semester of calculus is. Antiderivatives. Think you can handle it? Can you do regular derivatives? Sure. Then if you can do regular derivatives, you can do antiderivatives.
You say that now, it's not that easy.
So an antiderivative, so a function f is called an antiderivative, shh, guys, of f. So notice I'm not using f prime now, I'm calling it regular f. So my derivative, if my derivative is little f, the antiderivative, we don't know how to go backwards from little f, right? So we use a capital letter. So that's why it's important to use like lowercase f whenever you're talking about your functions, because the antiderivative is going to be capital F. So the function f is called an antiderivative of little f if capital F, of course I just made that look like a little f now, so I got to erase it. So capital F prime of x is equal to f of x for all x in the interval. So question, what is the antiderivative of f of x equals 2x? Yeah, what do you take the derivative of to get x squared, or to get 2x? You take the derivative of x squared. Is that the only one? No, you could have had x squared plus 1, x squared minus 7, x squared plus 10, right? You could have lots of things. So we say x squared plus c.
It's capital C.
So it says if f is an antiderivative of little f on the interval I, then the most general antiderivative of f is capital F of x plus c, where c is a constant. Do not forget the plus c. I remember I did that on an AP Calc test when I was in high school. Every single problem I forgot the plus c, but my teacher was very nice. He just counted me off 1 point. So he got me a 90. I had 99 over 100, and I was a point piranha like Julia back there, and I was so mad that I got a 99. He should have counted me off every single problem. Why was I mad about getting a 99?
See, there's some
I don't know.
over 100. Asking why did
I was not walking around saying I'm failing the class, though. Alright, so find the most general antiderivative of each of the following functions. So if you have cosine of x, so it's hard, you really have to know your derivatives, because now we're going to go backwards, right? So what do you take the derivative of in order to get cosine? Yeah, so you say capital F of x equals sine of x plus c. So if I had f prime, if I instead had written f prime of x equals, for the next one, sine of x, then when I go backwards, I put f of x, right? Little f of x. So be careful with your notation. Maybe I already have f prime on the homework. Then your new thing's going to be little f. So this is going to be capital F of x equals, what do I take the derivative? Negative cosine of x plus c. This next one, okay, so what it's saying is what if you have like x squared? What did you take the derivative of in order to get? So let's talk about the power first. So if I have f prime is x squared, what was f of x originally? It was something with x to the third. What's going to get rid of the third?
2/3.
Not 2/3. 1/3. So what's our formula? If I have x to the n, I need bigger. I need x to the, sorry, I did g prime. Is that annoying you? Sorry, that should be capital G. All right, it's going to be g, or it's going to be x to the n plus 1, right? Add 1 to the power, because originally we subtract when we do the derivative. Not 1 over n. 1 over n plus 1, exactly. Plus c. So you add 1 to the power, you divide by the new power. That's the rule.
That's terrifying what you're saying.
So if I add 1 to this power, add 1 to negative 4, what do I get? Negative 3. Do 1 over the negative 3 out front. That's our antiderivative. Add 1 to the power, 1 over the new power.
Are we going to have antiderivative drills?
Just derivative drills. That'd be too confusing. All right, so 5x to the 4th minus 6. Okay, so typically when I teach people these, I just say for the first few times you do this, just leave the 5 out front, and now take the antiderivative of x to the 4th. So x to the 4th, we do x to the 5th, and we do a 1/5 out front, right? Its derivative, 1/5 x to the 5th, would be 1x to the 4th. So we're good. What about the 6? 6x plus c. So our answer is going to be x to the 5th minus 6x plus c.
Why can't the plus C just be like implied?
Because if it's implied later and you like forget it in some of these story problems, it's not going to be good. It would be terrible. All right, so f of x equals, the plus c will basically, here's a real life example of the plus c. Okay, let's say it's getting pretty cold out these days. It's the end of October. I don't know what happened. How is it the end of October already? But, you know, it's pretty cold outside. Let's say it starts to snow. And when you wake up in the morning, we have 10 inches of snow. So let's say we have 10 inches of snow. But over the course of the day, it continues snowing. And it builds, and it builds, and it builds, and it's snowing all day long. And we gain an additional 7 inches of snow. How much snow do we have?
A lot.
How much did we start out with? 10 inches of snow, plus an additional 7 inches of snow. So we have a total of 17 inches of snow. That 10 inches of snow is going to be your plus C. It's going to be your starting amount. So it will be important later on. I know, we do have a brigadier general as our assistant head of school. We do not often Cancel. All right, so how about this one? So I have the x to the fifth. What'd you guys get for out front? 3/5, exactly. Plus x to the fourth. What did you put out front? 1/2, because the 2 is kind of hanging out in the front, and I have 1/4. 2 times 1/4 is 1/2. Minus 5x plus c. This is Alex's favorite thing that we've done all year long.
Isn't there some sort of
Is that
like
it?
something plus c or some sort of single thing to remember?